Hello, everyone. Welcome back to Codex. Today, we're happy to feature a talk from Caroline Moosmüller from the University of North Carolina at Chapel Hill. Caroline is an expert on geometric data analysis, computational optimal transport, numerical analysis, approximation theory, as well as applications in biology and medicine. Today, she'll be talking about learning in the space of probability measures. Take it away, Caroline.
Okay, thank you so much for inviting me. I'm very happy to speak in your seminar. This presentation is about learning in the space of probability measures, so learning in the sense of machine learning or learning algorithms. And I know that a couple of other people have talked about similar things in your seminar. So I think you have had Alex Cloninger and also Keaton Ham. So this is a lot of overlap with what they talked about, but I will also try to talk about a new topic, which is trajectory inference. Anyways, I will have an overview. So, okay. Just a minute ago, the slide advancing worked. Now it's not working anymore. So here's the overview. Okay. Let's see if it works now. Okay, now we're good. So this is the overview of my talk. I will first talk about settings in which we want to think about data as probability measures. These are just a few examples to motivate why we're thinking about learning in the space of probability measures. And then I have 3 topics prepared. From my experience, I might not make it to the last topic, just because for time constraints, but I do have some slides in case we can make it or there are some questions. So I will talk about 3 things that I'm interested in: trajectory inference, manifold learning, and linearized optimal transport. And then the last slide is just about a summary. Okay, so why would we be interested in data as probability measures? So here are a few examples of when you might want to think about your data as a probability measure, or in a discrete setting, a point cloud or a histogram. So on the very left, you have the bag of word problems, where we think about a text document as a histogram of how often each word appears. And then you might want to compare text documents based on the histograms. So this is a discrete version of probability measures. Similarly, in the middle, you have point clouds in the sense of thinking about gene expression data. So each point represents one cell in gene expression space. So the coordinates are different gene expressions, and each point represents one of the cells. And then for each person, you might have many cells, right? If you do single cell analysis. So each color you can think about as, for example, one person giving rise to one point cloud. And then you can ask questions about, how similar or different are 2 people based on their gene expression data. And, a way to do that is comparing the point clouds that come from different people. In this case, point clouds considered as discrete versions of probability measures. And then I have 2 examples of images. The left example with the monkey, this is basically saying we can think about the color distribution of each image. And then you can, this is the bottom picture. You can think about how to superimpose color of one image onto another image. And, if you Google this a little bit, you will see a lot of nice artwork that has been done in this way. Similarly, we can think about images as intensities over pixel grids. So this is what the number 7 is showing. So basically a density function. So all of these examples fall into the broader setting of thinking about data as probability measures. So in this case, I'm writing μk. And you can imagine we have n of those. So like n images or n patients with gene expression data or n documents. And, we want to do classical learning algorithms. So for example, if we talk about the gene expression data and some of your patients have a specific type of cancers and others don't, can we run a classification algorithm that figures out, which patients have what? So this could be an unsupervised or a supervised learning algorithm, for example. So the specific thing about this whole thing is that your data is not Euclidean as what you would usually think about, but your data is, a probability measure or point clouds sampled from that probability measure. And we still want to do these learning algorithms. So at the bottom, I wrote 2 examples of learning algorithms. So one, it would be supervised learning, where you have some labels known. For example, for some patients, their status, if they're healthy or not. Or for some images, this is a 7, this is an 8. And for others, you don't. And then you want to learn basically the labels of the unknown images. And in unsupervised learning, you don't have any labels. You just decide based on a distance how close or far away 2 data points are. And then, you cluster based on that. Okay, so again, the motivation is different type of data, different space, but similar types of algorithms. And obviously, what we need is a good distance, d, and there's many ways to do that. Today, I will focus on the Wasserstein problem because this gives you a very nice geometric setup and allows you to develop a lot of theory about algorithms. But it doesn't have to be Wasserstein distance. So I just want to mention that this is a particular geometric choice that we're making in order to develop our algorithms. But there's other ways to compare probability densities. Okay, so far about the motivation. Here's the one slide, quick introduction into optimal transport. So if you have never heard about this, it might be a little bit short, and if you have heard about it in the past, it might be too much. So just bear with me for trying to explain in one slide what Wasserstein distance and what optimal transport is. So essentially what I was just saying on the last slide, we want the distance between our probability measures. And one way to do that is with the Wasserstein distance. This is a W2, which is in the middle. And essentially the idea is to figure out how much does it cost to move one probability measure into the other. So at the top, you see an image of mu and nu, where mu is basically moved into nu with this arrow. And the question is, what is the best way to do that? And the best way in this setting, in the Wasserstein setting, is in the sense of optimizing for the effort that we need in order to move things. So here, the effort would be, how much work is it? How much does it cost to move the point x, or the mass in the point x, from mu into the point y of nu? And the cost is basically the distance of how far you have to move your mass. So this is the tx minus x squared, multiplied by the infinitesimal amount of mass that you're moving. And then by integrating over the entire space, you get the full cost. And now we're looking for a map that minimizes the entire thing. So this is one formulation of the optimal transport, or the Wasserstein problem. And of course, there's also a discrete version. This is what you see at the very top. So instead of smooth probability measures or continuous probability measures, you can think about point clouds and an optimal matching between the point clouds in the sense of cost. So the plot shows you one way to optimally match in the sense of Euclidean distance. Okay, so this optimization problem has been studied a lot. So we need some assumptions in order to make sure this actually exists, which is, for example, absolute continuity of the 2 measures, which we're going to assume. And we get 2 things out of it. One thing is this Wasserstein distance, which just tells you how much does it cost to move mu into nu. So it's a value, it's a positive value, or 0, in case you have the same measure. And you also get a map, which is the argmin, so the optimal map that moves one measure into another. The reason first of all, the map is not unique, but up to additive constant, it will be unique. And the reason I'm emphasizing this is because we're going to use the map. There's a geometric meaning for the map, which is essentially, if you want to do some kind of Riemannian-type geometry, the map will be a tangent vector. So this is one of the important features that we will need later. Okay, so as I said, this is very well studied, and you can find many textbooks on this topic. And this is the reason why we wanted to use it for learning algorithms. We have all of the theory and we have a lot of geometric properties. Like, as I mentioned, there's a way to talk about tangent spaces. There's a way to talk about interpolation and things like that. So this is why people like it. Okay, computation can be a problem. So computing the optimal map as well as the distance can be slow. So usually if you take the problem as I just wrote it, it's a linear program. And if you think about unsupervised learning algorithms, like I mentioned before, meaning that you have to do a lot of pairwise distances for your algorithm, this can become, computationally expensive. So it's always good to think about ways to reduce the computation. One way is the well-known paper by Couturi about the syncon algorithm, but there's other approximation algorithms as well. Just want to mention that. So computation is an issue with this problem. Okay, so now that we talked about this, the data we're interested in, probability measures, and the geometric framework in which we're going to consider this data, I want to give you a quick overview of the topics I'm interested in, and then we'll see how far we can get. So this is just one overview slide. So the talk is called Learning in the Space of Probability Measure. P over Rn is the space of all probability measures, and we're going to consider it with the Wasserstein geometry. And we are really going to do Rn for now as the support space. It doesn't have to be in order to do optimal transport, but for now this is a convenient setting. And the theoretical challenge to some extent, the technical challenge is that this is for one a nonlinear space, but then also an infinite dimensional space. So this makes it more complicated than doing learning algorithms in Euclidean space. Okay, so what are the topics I'm interested in? One of them is called the linearized optimal transport. So this is a way to deal with two things essentially. One thing is to make computations faster. So if you want to do a lot of pairwise distances, you can essentially instead of doing all Wasserstein pairwise distances, you can do more distances by doing distances easier by going into the tangent space. So computing linear distances that approximate the nonlinear distances. So this is one way to use it. The other way is for supervised learning algorithms. So basically what you should imagine, and this is not an accurate plot, obviously, but if the blue thing is your Wasserstein manifold, so the space of all probability measures, and the orange thing is your tangent space in one of these measures, then what you could do is take all of your data points, move them into the tangent space, and then do a linear learning algorithm in a tangent space. So this is essentially the idea. And I think you might have had a talk about this at some point in Codex. Okay, another section I'm interested in is manifold learning. So, this is a very well-known field where the extrinsic space is Rn. So you sit in Rn and you have, a finite dimensional Riemannian manifold. You have samples from it and you try to figure out what the manifold is. And here is like the more well-known Swiss role, which with manifold learning you can identify as a two-dimensional flat object. And now the equivalent question is, what if your surrounding space is the space of probability measures? So again, it's infinite dimensional. And you're looking at a finite dimensional manifold, which is, I haven't defined that, but let's say this exists. How can you learn that thing? So like a Swiss role in the space of probability measures, something like that. Yeah, so this is a second topic. And the third one, which I will actually start out with when I talk about more details later, is trajectory inference, which means that you have probability measures that change over time. So the way you should interpret this plot is by thinking about time going from left to right. So the black dots is the initial point cloud, and then they split into the red point clouds, and then they merge again into the orange point cloud. And the question is what happened in between as this time progressed. So essentially, it's an interpolation or approximation problem, but now in the space of measures or probability densities. So it's, it's an interesting kind of approximation problem. Okay, so these are the 3 areas I'm interested in. I have slides for all of them, but we'll see how far we will get. And then there's also, some practical stuff that we have to consider, which is the second part of this slide, which just says, even when we are able to do all of the things that I just mentioned, we still have a computational question, which is we have to compute these optimal transport maps and the Wasserstein distances, which can be intense. And also sometimes we have to ask a question, is it really meaningful, like the output that we're getting? So one thing I'm interested in is something which is called sliced optimal transport, which I will not talk about today. I just want to mention as an interesting topic, which essentially says, solving high-dimensional optimal transport problems is complicated. So let's slice it down to 1 dimensions. And in 1 dimension, it's a very easy problem. And then glue it together to create something in higher dimension. It's not really optimal transport, but it's related. And you can do a lot of things with it. Another thing I'm interested in is learning maps which are not necessarily optimal transport maps. Just sometimes, we might have more information than just the 2-point clouds. We might also know something about additional structure, and we would want to add that into our learning algorithm. So sometimes the optimal transport map itself is not good enough, and we want to do a little bit more. So this is what I mean with learning maps. And then, of course, this is a very general framework. It just says applications. But there's a lot of ways to think about how to use this kind of framework in various applications. And one of them I mentioned is, for example, gene expression data and thinking about different cancer types. Okay, so this is my short overview. And now I would start talking about trajectory inference. And just pausing for a second if there's any question. Okay, that's good. It reminds me of my calculus class. People are also not asking questions, so we can postpone. Okay, so let's get into the second section. So I will start with trajectory inference because I think this, is one of my newer works, and I think has not been presented in this seminar. Okay, so what is the problem? The problem is we have point clouds or probability measures which evolve over time. So again, time goes from left to right. You started with the black point cloud and you end up in the orange point cloud. And the question is, what happened in between? So you only see those, those point clouds, and also all of the points look exactly the same across all time steps. So you cannot distinguish between the points. So it's not possible to track one individual particle. They will all look the same. So this is why we're asking the question. So the question is, what is the most likely thing that had happened as time progressed? So here's like one suggestion, right? So for each particle, we want to figure out what is the most likely path that it took. And here's like one example. And there's no, if you have no additional information other than here are the point clouds and here's the time steps, then, there's many ways of solving this problem. It's not a unique way. With optimal transport, we can say we want a cost minimizing way to do that. So for example, what I drew here is not cost minimizing because some of the particles move around quite a bit and we want basically to minimize the movement. So with optimal transport as a way to think about it, but it's not the only way, obviously. And there's a very interesting paper by Jeffrey Schiebinger, I just want to mention this here, that uses this idea to understand the development of cells in gene expression space. So there are some applications of how to use that. Because when you do single cell measurements, in every measurement, you will essentially kill the cells. So it's impossible to follow one individual cell. You can only follow the trajectories over time of different cells. And so you have to figure out, if this cell had still been around, where would it have moved? Something like that. Okay, but on the mathematical side, the problem we want to consider is time evolving measures. So you have discrete points in discrete time. These are the t's, and then for each time step you have one measure. And we want to figure out what would be a good curve that either interpolates the given points or approximates them, where approximation, can mean different things. But for example, close in Wasserstein distance. So this is really a classical problem in interpolation approximation. But somehow the new technical aspect is that we're not doing it in the Euclidean space, but we're doing it in the space of probability measures. So again, a nonlinear infinite dimensional space. And what I'm going to show you is one way to do that. If you Google trajectory inference and Wasserstein space, there's a lot of papers. So people have worked on that. We tried a new approach for which we think has some advantages. Namely, the algorithm is fully intrinsic, which means we're never leaving the Wasserstein space. And is not dependent on the support space. So right now I'm saying the support space is Rn, but really for the algorithm it doesn't work. If the measures are supported on a different space, it would still work. Okay, the scheme is based on B-splines, which is a common way to do interpolation approximation in Euclidean space. And it can deal with non-uniform mass. So what that means is in the plots above, I just have each of the points has the same amount of mass, so there's uniform mass. But you could think of problems where some of the points have more mass than others, and we have a natural way to deal with that. Okay, so how does it work? It's actually a very simple algorithm, and the only thing we're doing is replacing things that are Euclidean with things that are Wasserstein. So this is the idea.
Sorry, Caroline, could you go back a slide?
Yep.
So when you talk about trajectory splitting, like intuitively, I can see the split in the picture where it branches out, but like how is that formulated like mathematically?
Oh yeah, that's a good question. I will show you a picture later of what it looks like, but there's not really a math formulation. But essentially, what you can think about is you have a line which transports a certain amount of mass, like a thicker line, and then the thicker line branches out into some smaller or thinner lines. So that the sum over all of them is the original mass. This is what you can imagine. Anyways, there will be a picture, but I don't have a math formulation for you. I just have a picture.
Okay, thanks.
Okay, so let me describe the algorithm and then we can look at non-uniform mass and splitting. So this is a very old, well-known algorithm called the Lane-Riesenfeld algorithm. I just want to mention we don't have to use this specific algorithm. There's others that work in the same way and do a similar thing. This is just to highlight one idea. And the Lane-Riesenfeld algorithm is an iterative scheme which is known to converge to B-splines on Rn. So when your data is in Rn and you apply the algorithm, you will get a B-spline as the output. And also I want to mention it is a non-interpolatory algorithm. So what that means is we're not going to interpolate the data, we're going to approximate it. If you want to do interpolation, there's other algorithms that can do that and work with the same idea. I'm just to make sure this is clear. Okay, so what does it do? Essentially what you see in the picture is on the left, we started with a square, or we started with the corners of the square essentially. And we applied one step of the algorithm, and what we get is the thing at the very right, which is basically a cut-off version of the square. So this is why it's also called corner cutting. And then you can take this object at the very left, cut off corner, and repeat, cut off corners again, and then repeat again. And what will happen in the limit is you will get a smooth circle that approximates the original square. So this is the idea. It's an iterative scheme that produces, in the limit, a smooth smooth to some extent curve that approximates the original data, which in our case is the corners of the square. Okay, so how does it work? It has two steps. Step number one is take the points that you have and double them. So this is what you see on the very left. And then step number two, compute an average. So compute midpoints between given points. This is what you see in the B image. We needed the doubling so that we can keep the corner points, essentially. Because if you compute the midpoint between the point with itself, you get the point back. And then we compute an average again, which is the C image, and then throw away the old points and just connect the new points. So this is the Lane-Wiesenfeld algorithm of degree 2, because we're doing 2 steps of averaging. You can do multiple steps and you get smoother curves in the end, but this is just one example. Okay, and then imagine we repeat this forever. We do a limit and the output will be a smooth curve. So the important thing here is the only thing we're doing is double points and computing averages, which is a midpoint. And you can do exactly the same thing when your data is point clouds. So instead of Euclidean points on a square, we now consider point clouds. So this is the bottom one. On the very left, you see point clouds evolving over time from left to right. Black is the first point cloud, dark red is the second point cloud, light red is the third point cloud, orange is the fourth. And we can use exactly the same idea. So basically double point clouds and then compute average between point clouds. And what is the average between 2 point clouds? Essentially what we do is we take the 2 point clouds, we compute the geodesic that connects them, which is basically done with optimal transport. So you compute the optimal transport map and it will give you a geodesic if you multiply it with t, essentially. So essentially the formula here at the bottom, it's identity plus the optimal transport map between 2 given point clouds. And then you just evaluate in the middle, which is t is equal to 1/2. And you push your measure with that. So geodesics in the Wasserstein space is a very well-known concept, and we just make use of that to find a midpoint by evaluating the geodesic at t is equal to 1/2. And then the same algorithm runs. You just need doubling, and you need the geodesic midpoint, which can be computed in optimal transport. And what you see at the bottom panel is multiple iterations of this idea. So the very left is like 1 or 2 iterations. And then as you increase the iterations, you get more and more point clouds in between. And as we approach a limit, we get all of these trajectories, essentially. Okay, that's it. So this is the algorithm. It's not very complicated. I will give you some ideas about that in just a second. Just a note, as we mentioned, this is not interpolatory, so we're not hitting the point clouds exactly. We're just getting the shape of what they look like. So it's approximation. And this data is uniform. So there's no splitting, as we talked about before. So all of the data points have exactly the same amount of mass. So you really get trajectories in the sense of curves. Okay, so here are some more thoughts about this. This is a comparison to other methods. If you want to see more comparison also with numbers, we have them in the paper. We did a very comprehensive overview of all of the algorithms that exist out there. This is just to give an idea. So the very left picture is a neural network approach, which is basically a flow matching approach, which has some problem with the different modalities to some extent. In the middle, they're using a different geometry, Fisher-Rao, which changes the problem a little bit. And our algorithm is the very right, which uses, as I just said, the Wasserstein geometry. So you can get different kind of pictures depending on which geometry you're using. So for the middle one, I just want to mention there's some kind of, intersection of trajectories if you look at that. And also like the trajectory in the middle might be a little bit unnatural. Okay, so what do I mean by splitting? This is the plot that I was talking about. So if you have mass that splits, so we start again on the left with time and we end on the right with time. So in the beginning, you have one big blob, and then in the next time step, the blob has, split into two, and the next step, the blob has split into three. So, something happened in between. And our algorithm, without knowing about any of this, we just plug in the data. We don't tell it you have to split. What it does is it naturally starts with two trajectories, which then split into three. Right, and this is what I meant with natural splitting. So when your data is of that form, we can naturally reproduce that in the way the trajectories are built, which other methods are not able to do. And then we also did some applications for something which is called supercell data. So when I talked about gene expression data, and you think about the plot from the very beginning, we were thinking about point clouds where each point has the same amount of mass. And now what we're saying is, or not what we are saying, what people are sometimes interested in is taking individual single cells and merge them together into a bigger supercell, for example, when they're very similar. And the way we should then think about this data is this merging creates a bigger point cloud, or a bigger point with more mass. This is the right description. So what you see in the picture on the right, for example, the orange dots is one time step, and you can see the points have different sizes. This means more or less gene expression has been merged into one. And the different colors mean different time. And with our method, if we have this kind of supercell data which evolves over time, we can still infer trajectories and don't have to worry about the fact that the data is non-uniform. Okay, there's also some theory, and I haven't mentioned any co-authors on the first slide because there's many for all of the projects, so I will just mention them now. So this is work with my student Amartya Banerjee, Harlan Lee, Nir Sharon, published in AI Stats this year. So basically, what we showed is this algorithm converges to a limit curve. And you will not be surprised that the convergence rate is 2 to the minus r, where r is the number of iteration steps. And why is not surprising? Because we're doing midpoints in every step. So, there's a fraction 1/2. So what is what does this theorem say? So if we do our iterative scheme in every step, we get more and more point clouds. And for a fixed step r, we are connecting the different point clouds with piecewise geodesics. Again, geodesics in the sense of optimal transport, so using optimal transport maps. And this gives a map nr. And as r goes to infinity, so as the refinement level goes to infinity, we will converge in the sense of functions. So function from t, which is time, into the space of probability measures. We will converge to a function and infinity in the Wasserstein 2 sense. So this basically shows that, this algorithm, the Lane-Riesenfeld algorithm in the space of probability measures, does give you a limit curve. And this is what we see in the pictures, essentially. Okay, the key insight of this whole thing is you don't really need the Wasserstein space. The whole proof works for any complete metric space that has the geodesic property. So, the original Lane-Riesenfeld algorithm was framed in Euclidean space. We were motivated by the Wasserstein space, but really it is much more general. So you can do any complete metric space with geodesic property. And something we're interested in right now is so for the Lane-Riesenfeld algorithm, it's known that it produces B-splines of a certain degree, with certain smoothness. And we don't really have a good way to talk about that in Wasserstein space. So this is something we're interested in. So first of all, what is the smoothness to some extent? Or what is the meaning of smoothness of these curves? And the other thing is, what is the limit curve? Is it a B-spline in the sense of what we consider B-splines, and what is the meaning of B-splines in Wasserstein space? So this is some of the future work we're interested in. Okay, so this concludes the trajectory inference, and I would be moving on to something about manifold learning, which is a little bit of a different topic. So yeah, sorry, I think there was a question.
Yeah, so if I'm understanding this right, this is after you're doing all of the, all of the corner cutting steps, then that's going to converge to a limit. But suppose you had two different samples from the same probability distribution. Are you able to like use any sort of concentration of measure type things to get that those two limits are going to be the same for the different samples?
Oh, so you mean if I have, okay, so we have, let's say we have n measures in the beginning, black to orange, and we sample from them, and then we take different samples and we apply the algorithms to both of them. And then the question is, does it give the same limit curve?
Yeah, suppose you had two different research labs, they do the same experiment, but they do it in parallel. Will you get the same, and you run your algorithm on both of their data, will you get the same thing more or less?
Well, so if you run on a discrete data, no, because it depends on the sampling. Just from pictures, you can see how it depends on the sampling. But yes, so as you said, if the sample come from the same smooth measure, and we were to run the algorithm on the smooth measures, then you would get the same result. So basically in a limit, you would get that as in a sampling limit, but not in the discrete setting, it would look different.
Okay. Yeah, thanks.
Okay, very good. So this is the trajectory inference. Let me talk about manifold learning. So this is a little bit of a different flavor. So forget about time. There's no time anymore, no trajectories. This is just about probability measures. And I will also start with one particular algorithm, as I did with Lane-Riesenfeld. The whole thing is more general, but in order to explain the idea. So again, if you have never heard about manifold learning, which I don't assume for this audience, but let me just motivate with one algorithm, one particular algorithm, which is not necessarily really manifold learning. It's just about distances. So this is a depiction of the multidimensional scaling algorithm, which is essentially saying, if you're given data and you compute distances between the data, so for example, you're in Euclidean space and you do Euclidean distances, this algorithm will give you an embedding of your data just based on the distances. And usually you want a lower dimensional embedding, such that the distances are approximately preserved. So what you see in this picture is if you have data point A and data point B, the red and the blue one, you're only given the distance between them. The algorithm will give you an embedding such that the distance is preserved up to global operations. So this is essentially what you have to do. You take your distance matrix, you move it, and then do a eigen decomposition, and then use the eigenvectors as an embedding. So this is one way to do it. So what we were thinking is, okay, so it's known that when your data is Euclidean and you have Euclidean distances, this will work very well. It will reproduce the original distances. But what if your data is not Euclidean distances? What if your data is not Euclidean, but it's point clouds, and the distance you're plugging in is the Wasserstein distance? This is a very natural extension of the same idea, right? And you can do the same algorithm. Just plug in a different distance matrix and see what happens. So what we're doing is pairwise Wasserstein distances, and your data, which you can see on the very left, is, for example, Gaussian measures. So I just have to explain exactly what this picture means. Each of the Gaussian plots, so each of the blobs in the same color, is considered one data point. So the Gaussian itself is one thing. And then we compute between Gaussians the Wasserstein distances, the pairwise Wasserstein distances. feed this into the same algorithm, and look at the output. And the output is what you can see on the very right, which is just individual points on the grid, which is not very surprising. So it essentially gives back the original, the parameters that defined the original data. Okay, so why does it work? Well, in this example, it works because the data itself is isometric to Euclidean data. The Wasserstein distance between two Gaussians when the covariance is the same, which is the example here, is just the distance, the Euclidean distance between the means. So really, this is a Euclidean problem. And therefore it works. But this is, the initial step to motivate the problem. And so, we want to move a little bit, beyond that, because this is not a very interesting case. It just says when your data is isometric to some Euclidean grid, then MDS works in the same way as you would expect. So what happens if we go a little bit further away and say, we have an error in the way we compute the distance, and we have an error in not being exactly Euclidean. So it's not like this nice grid with the Gaussians, but there might be some small curvature that goes into this manifold. And this is the theorem. And what I had mentioned before, so together with Alex Cloninger, Keaton Ham, and Varun Khurana, we were studying this problem. So what we're saying is you have your data points, mu I, which is your which you can consider as samples of your manifold. But they are very close to what we would consider the grid on the last example. So we're saying they are t tau isometric to lambda, where lambda is Euclidean. So think about the grid with the Gaussians, but there's a little bit of error, which is tau 1. Okay, and then we're computing pairwise Wasserstein distances between our data points, but we're making an error while doing so. Why would there be an error? Well, this is what I mentioned in the very beginning. Computing Wasserstein distance is expensive, and usually people use approximations to the distance, like the Syncon algorithm or linearized optimal transport, which I haven't talked about yet, or a combination of the two of them. And so if you do that, you will not get the exact Wasserstein distance. You will get dij, which is, tau 2 close to the true solution. And now the result says the following. If we feed this error distance matrix, the dij, into MDS, we're going to get embedding points in RD, and they are close to the thing that we are isometric to, almost isometric to the lambda. So you can think about the grid, but it's not exactly the grid because we had some error in the beginning, and the error is reflected in how close we are to the grid. Namely, we get a constant tau 1 and tau 2. So this is essentially the result. So it says, if you have your Gaussians on a grid, but then it's not exactly that thing, but a little bit of an error to it, and you're not making your computation in the best way possible, you can still get an embedding that represents the original problem up to an error that depends on tau 1 and tau 2. Okay, so tau 1 basically depends on your data. You can't really choose what that is, right? Tau 2, on the other hand, depends on the algorithm you're using to compute the Wasserstein distance. So we do have explicit bounds on what tau 2 is, and I didn't put it here because they're very long. But essentially what we study is this linearized distance, which is here with the F sigma, which I haven't defined, but essentially says go to the tangent space and compute linearized distances and see, how well that approximates. This is an eigenvector eigenvalue perturbation result because of the way that MDS is done. And one important note, which should motivate the next slide, is we're using extrinsic distances. So when I say compute the Wasserstein distance between mu1 and mu2, so between the Gaussians, this is really the extrinsic distance in the space of probability measures. While if you think about manifold learning in the Euclidean space, you would want to use the geodesic distance on your manifold to get a better approximation of the distance between the points on the manifold. So what we are starting here is really flat problems. So the problem I showed you before, Gaussians on a grid, isometric to Euclidean case, or Gaussians on a grid up to some small error, which is almost a flat problem. So the obvious question is, can we extend that to geodesic distances and curved manifolds? Okay, so this is the next slide, which just explains this idea. Okay, so this plot is in the Euclidean space. This is again the Swiss roll, which we all know. So the left-hand side shows you, the Swiss roll, samples of it, and the right-hand side plot shows you an embedding. We don't have to talk about MDS anymore. It can be any algorithm that essentially is based on distances. And what you would like to do is use the geodesic distance on your Swiss roll to get the flat object back. And you can compute that by you can approximate it by graph distances or something like that if in a discrete setting. And we can do a similar thing in the Wasserstein space. So this is a Wasserstein example. It's not very clear what this exactly means, but I will explain. So essentially what you should think about is we have a curve in three-dimensional space, and each point on the curve we consider as the midpoint of a Gaussian. So we take the curve, all of the points are midpoints, and then we put Gaussians on the curve. This makes it into a Wasserstein problem. It's not a very exciting problem, but it is a more complicated problem than what we just looked at before because there's some underlying curvature. And if we now compute Wasserstein distances between the Gaussians, the output of, for example, MDS would give you a straight line, as you can see on the right-hand side. So it would identify this thing as a one-dimensional problem. But again, we're using Wasserstein distances, which are extrinsic. So, and I'm also talking about Gaussians, which means, again, the Wasserstein distance is just the Euclidean distance between the means, which would approximate the geodesic distance if the points are close enough. So it is a little bit more complicated to what I talked about before, but not really. So the question becomes, how can we do a geodesic distance on the space of probability measures? So we have omega, which is considered some kind of submanifold. And you can do it in a very similar way as in the Euclidean setting by just forming a graph where each node of the graph is one of your measures. And then you can do like a shortest path kind of problem. And then to actually use all of these manifold algorithms, we have to think about discrete to smooth, right? So if you have your submanifold and you have points, discrete points on a set manifold, you build this graph. Is there some kind of convergence, and do the distances converge and things like that? And of course, if you want to do something more advanced than MDS, you might want to think about Laplacian operators. So these are questions, which we partially resolved in a recent paper, where we have, yes, so this is the main citation. There's no citation, okay, but this is the main setup. So that this was recently published in the Siam Journal on Mathematical Analysis. So essentially, together with Keatonham, who I think is well known in this community, and also Matthew Thorpe and Bernhard Schmitzer, who I wanted to mention as co-authors. So anyways, what we're doing is we're saying you have a model of what your omega, your submanifold in Wasserstein space, is allowed to look like. Namely, we want it to be finite dimensional so we can better deal with it. So the extrinsic space is infinite dimensional, but we want something to be finite dimensional. And so the way we think about it is by saying you have some kind of finite dimensional Riemannian manifold, and then there's a way to move it into the Wasserstein space. This is the epsilon. And there's a lot of assumptions to make sure this makes sense. So it's not just, a map that moves, but you also have to make sure the distances don't explode, and you have to make sure that the tangent vectors move in the right way. But essentially what you can think about is the omega is the midpoints And the epsilon omega is when you put the Gaussians on the midpoints. So this is the kind of way to make a Euclidean problem into a Wasserstein problem. And for this setting, we are basically able to describe geodesic distances and describe the convergence of graphs. We haven't worked on the Laplacian operator, but this is something that works to some extent. And with all of this setup, we can basically talk about manifold learning algorithms in the space of probability measures. Okay, so is the talk supposed to be 1 hour exactly, or should I come to an end soon? Okay, if there's no feedback, I will just talk about one quick application and then maybe come to an end. So the application, which is actually before I did all of this work on manifold learning in Wasserstein space, is motivated by gene expression data. So this was in collaboration with Memorial Sloan Kettering Cancer Center, and this somehow motivated all of these theoretical work that we were doing. So let's say you have a data matrix that consists of samples versus features. So sample in this sense, you can think of patients, different people, and features, you can think about gene expression data. And in this study, we looked at cancer and connected tissue, so gene expression data of different sarcoma types. And what we wanted to do is figure out a way to classify the data in an unsupervised way. And the classification wasn't necessarily about classifying, by label which sarcoma it is, but by trying to figure out which sarcoma or patients are similar based on the gene expression data. Okay, and we did a Wasserstein type of approach for that. So what we did was we took a gene network. So this thing, the way you should think about it is each node is a gene, and each edge tells you when 2 genes activate each other. So red in this case means non-active and green means active. This is just an example. It's not exactly what things would look like, but this is how you should think about it. And we chose particular genes which were of interest to this sarcoma, or in general to cancerous data. So for example, the middle node, the important one, is the so-called p53 gene, which is one of the most important tumor suppressors. Okay, so what you can think about is for every patient, we have the same network, the same graph, because they all have the same genes, but the activation of genes is different, and this is based on the data that we have on the left. So the more you can think of this, the gene expression, as a function over the nodes, essentially. And then we were saying, okay, so we have all of the same networks and then different function over the nodes. What is a way to do, pairwise comparison between patients? And one way is to compute the Wasserstein distance. So if you take the function over the gene network and you normalize it, you have a probability density over the gene network, and then you can compute the Wasserstein distance. The only thing you have to be aware of is the ground space here is not Rn, but the ground space is a graph. So the distance is not the Euclidean distance, but the distance is, for example, the shortest path distance or something like that. Okay, and then we have all of our pairwise Wasserstein distances, and we feed them into a manifold learning algorithm. And so in this case, we did a diffusion map algorithm. And what you can see in the right picture is, different colors, meaning different types of sarcomas. This was not information that we used for the algorithm, but it's somehow turned out that different sarcomas stick together in the embedding. And we then did a clustering algorithm on that embedding to find 4 coherent states. And 3 of them were known sarcomas, and 1 of them was a new signature, which was different types of sarcomas, but all similar gene expression data. And this was actually the finding of interest. Okay, so this is one application of Wasserstein manifold learning to gene expression data. This is obviously ongoing work, so this is, I think, a field of interest. But my work is mostly on the mathematical side. Well, mostly because this is my background. But I like to work with people from medical fields to get some interpretation of these data analysis problems. Okay, so I will skip the linearized optimal transport. If you're interested in that, I'm happy to talk offline, and I will just move to my last slide, which is the summary slide. Okay, so the summary says I have talked about 3 topics, which is not exactly true. I just talked about trajectory learning and manifold learning. And there's some ongoing research we're interested in. One of them is Gromov-Wasserstein problems. So this is my student Caitlin, who you can see in the middle. One is fMRI data, which is my student Aaron, who is also in the middle. There's many people in the middle. And then we have Amartya, who worked in the trajectory inference on the very left, Chu Chang-bo, who works on problems in independent component analysis. And on the very right, we have Xing, who has moved on, who was a postdoc in the group and is now in the University of Nebraska-Lincoln. And I recommend following her work as well. So yeah, thank you for your attention, and I'm happy to take some more questions.
All right, let's smash that reaction button. The recording could stop.